Hi, this is the first presentation of the Universal Asynchronous Receiver and Transmitter playlist, where we will look at the basic concepts underlying this type of circuits. After watching this presentation, I hope that you will be able to explain the operation of this type of circuits and also to describe the organization of the digital frames that are used with the RS-232 communication standard. So, as the acronym indicates, a UART is a digital block that can be used to receive and transmit information asynchronously in a variety of situations. And asynchronously in this context means that there is no common clock line, as you can see in this slide. The communication takes place in serial form, that is to say, one bit at a time. And the minimum number of lines needed are shown here. So we need a transmission data line, a receive data line, and a common ground connection. Well, actually, the standard RS-232 connector will have a larger number of pins, but the minimum number of pins that we will need to set up a successful communication is 3, as indicated here. The RS-232 serial communication standard has been developed more than 40 years ago, and it is actually a well-known example of a serial communication standard that uses a UART to carry out the serialization and deserialization operations that are required to transfer multi-bit words from one system to another. To give you an example, if System 1 needs to send 1 kilobyte of data to System 2, it will have to deliver 1 byte at a time to its UART, which will use its serializer to send 1 bit at a time through the transmit data output, which is connected to the receive data input of the UART that belongs to System 2. Because the RS-232 standard has been defined so many years ago, the transmission speed is typically very low, so this is not a feasible solution when we need to transfer large volumes of data. To give you an example, the typical value which we will use in our practical examples is 19,200 bits per second. At this speed, 19,200 bits per second, how long will it take to transfer 1 kilobyte of data from System 1 to System 2? Well, to answer this question, we need to know the frame format that is used in the RS-232 standard. And as you see in this slide, transferring 8 bits of data does not mean that we will send only 8 bits. Because the two systems do not share a common clock signal, we will need a way of synchronizing them whenever a new word starts to be transmitted. So the solution for this synchronization requirement is to use what is called a start bit, which is always a 0 and which marks the beginning of a new transmission. The start bit is then followed by a sequence of data bits, then by an optional parity bit, which is not being used in the example shown here, and finally by a stop bit, which is always 1, and which therefore leaves the data line at 1 after the end of the transmission. So this means that whenever the receiving part, say for example the one on the right, detects a logic 0 at its received data line input, it knows that the other part is initiating a new transmission. So we need to estimate where is the middle point of each bit period and to read the logic value that is present in the transmission line at those moments. Well, in the case illustrated in this slide, this process would have to be repeated 8 times since we have 8 data bits, starting with the least significant bit. The transmission in RS-232 always starts with the least significant bit. And then since we are not using parity in this example, the stop bit will immediately follow the most significant bit, and the transmission line will remain at 1 after the transmission of this stop bit. So a fundamental requirement to set up a successful communication using the RS-232 protocol is therefore to ensure that both parts share the same settings with respect to the number of bits per second, the so-called baud rate, and also the frame format which defines the number of data bits. They can be, according to the standard, 6, 7 or 8 data bits. The existence or not of parity and its type, if it exists, which can be odd or even, as indicated in this slide, and the total number of stop bits, which according to the standard can also be defined as 1, 1.5 or 2. And as I said, parity, if it exists, can be defined as even or odd. The total number of ones in the data bits and the parity bit itself must be even for even parity, or of course odd for odd parity. To give you an example, if a byte contains 3 bits at 1 and the parity has been defined as odd, then the UART will automatically generate the parity bit as 0, so that the total number of ones remains odd. And that's it. Thanks for your attention.